Welcome to day 17. So today we'll finally get to the core architecture of Grep. So in this video, I want to cover like the core functionality aspect in Grep and how I achieve it. Now I'm not going to go into all the details in all of these commits. You can do that later. I will just focus on the core aspects. So really there is just like two main things if you think about it. Because we started with find last and before we did this grep, we had this idea of walking the file system. So we need to do the same thing. So because I want to do a grep which is recursive by default, the way trip grep is, right? So we don't want we are not going to focus on single file grep. We want to focus on multi-file single directory grep. Now, so the way you can think about this is there are like two aspects to this. So there is first this requirement to walk the file system, right? Uh, so that is like the first thing you do. So the next thing you do is to actually grep each file that you come across, right? So this is the like two parts to it, if you want to think about this. And the main thing that I wanted to take away from these modern grep alternatives like ripgrep is to actually do this stuff in parallel. So I want to parallelize and use multiple threads as much as possible. So that's built into the core architecture. And the decision I've taken here is to do the first part serially. So I'm not going to do the file system walking in parallel, but we will start the processing of the actual tasks in parallel. So let me quickly show you, and then we'll be able to follow. So the core fs walker function, that's like the core thing to do the file system walking. What I'm doing here is it's going to visit a directory, and then it's going to visit all the directory and the files basically in that folder. And I've very explicitly separated out these two aspects because I want to do different kind of checks for files versus different things for walker for directories, right? So I mean it's obvious here. What we're doing is we're doing a recursive call. So for each directory we're going to call the same function again. So that's how we deal with directories. But for files, we will go ahead with the next thing, right? We don't actually process the file. So that is the difference here. So for now, if you see this queue file function is just empty, just printing out the files. So this is the core file system walking, but there's one more thing to add here, and that is the basically checks that we do for directories and files. So what I mean is ripgrep is very intelligent about the files it's managing. That is, it's going to skip files that you would not normally look into. For example, .kit folder or say node modules folder in a JS project or .vn in a Python project. So point is there are folders which there is no point going into. That's one of the ways ripgrep saves time. And the same way, there are also files which are not worth looking into. For example, hidden files or files which have certain extension, right? For instance, there's no point in grepping a PNG file and so on. So we can add a few checks here, both for directory and for files. So you see here in this commit, that's exactly what I've done. So for instance, in this commit, I have a small blacklist, which we have creating there manually, and it has the name of the folders. And we're going to use the member function to basically check if the current directory name is actually part of the blacklist. And if so, we'll just skip and we'll not do anything. And similar logic we apply for the last character. Here, for example, I want to not look at files that end with hash or tilde. These are files which are like intermediate files created by Emacs and Vim. So I want to just do a check, and if the last character of my file name is matching this, then I am going to like not do anything. I'm going to skip this file. So this is what goes into the core logic of the file system walking, right? Now I can even go to the latest version of my commit, and this is the same file system walker that we saw, except I've added a few more checks. So for example, I've added ANDER case to catch any errors, and if there's an error, it's just going to print out if there's and skip that directory, right? So that's the idea here. Now this is the core part, right, of walking the file system. But then the actual important thing is to process the files. And how are we doing this? So how is it being organized? And that's what you see here. So this is what like focusing on, and let's like clearly spell out the architecture thing that is going on here. So we have the main thread. So this is the main thread. I'm just using this to indicate the main thread. And if you see here in this code, one of the first things we do is we are going to create this workers, which is loop for I from 0 below number of workers, and we are collecting bordeaux-threads. So bt make thread creates a new thread using the bordeaux-thread library. I'll show you the API. Basically, this is the lowermost level of abstraction to be able to manually create threads. We're going to call the process task function in this thread. So you can think about this as like a few different workers which are going to be running, and basically we have set this to number of workers. This is what I talked about when we talked about the argument flag parsing. So when I'm saying 4 threads, these are the 4 threads, right? So there can be 4 worker threads. And now if you see in this order, I also have an extra worker called a print worker, that is yet another thread which is running a different function. So if I want to show it here like this, this is yet one more thread, right? So these are the workers, this is the print worker, and this is our main thread. And the first thing we're doing in the main thread is this fs walking, right? So we are spawning the other threads, and then we then do our actual walking. Now in this walking, you've already seen the code. Basically, we were adding the, I can show you the code for a moment. If you see in the walker, the actual files are being dealt with this function, queue file. This is where we were skipping the unrated files. The last thing we do is, we are actually pushing the name of the file. So this file is just a string to a particular queue. Here I've used the lparallel library. I'll talk about the library separately, but what this means is, if I go back to my diagram, this means that there is a queue. So you can think about it like this, and we are feeding things into the queue from our main thread. So basically, as each and every file is being walked over, each and every directory, that is happening from a single thread, but those files are getting added to this queue. Not the directories, right? The directories will just getting recursed with fs walker. The files are getting added to this queue. And later we'll see, maybe I can show you the actual process. So when we talked about the workers, we said that it's running this process task function. So in this process task function, what we're doing is, we are simply going to loop, and we are going to pop an item from the queue, and we're going to process that item. So if I go back to this diagram, what this means is, these threads are going to, each of them, pop an item from this queue. So there's one main thread which keeps adding files as it's walking the directory, and these 4 worker threads will keep picking out results, basically file names from this queue, and each of them will process that particular file. So the process is the actual grep function. So a particular file will be loaded and processed on a single thread, right? So once one of these threads, worker threads, starts working on a file that is trying to grep the lines within the file, it's only going to do that. And when it is done, it is going to pick up another item from the queue, right? So far so good. Now if you see, I also have this print thread, so I need to show you that. And the idea is that just to serialize my order of prints, because if not, each of the threads will print randomly, and there might be cases where the results override. And also for like performance reasons, at least that was my reasoning, I will push results. So if you see, for instance, this simple function, the file grep file disk. So what basically it does the actual code. This is the core grep. We'll come back to that. But at the end of it, it's going to take the result, and it is going to push the result again into another queue, the print queue. So this is where this part comes in. So there is yet one more queue sitting here, and the way this works is, each of these threads will push into the queue, and the print queue will pick one at a time entries from this results queue, and then print the results. So there is a bit of nuance here, because if you see here, it's no longer a string like we did with the file name. Instead, we're actually sending a file result structure. I'll show you that in a moment, where we track the name of the file and the result entry, which is actually a list, because it's like you need to know what is a line number, and on each line number there are actually multiple matches, so it needs to also have those individual matches. my grep, and if I try to do this grep again, you will see this was the flag that we added last time to show that the flags work. If you see, for instance, we need to print the line number, and we also need to color code the individual parts which match, right? So that's why the data structure between this set of workers and the print worker via this queue is different, right? You can use whatever data structure you want. Here it's simple strings. Here it's file search results, which are maintained in the queue. So the function you see here is what happens individually in this particular box, but let's talk about the rest before coming back here. Okay. So let's start at the very beginning, where we basically set up our queue, right? So basically this function, if you go to the definition, it's very simple. We just have two parameters, queue. So if I go back to the diagram, this queue and the print queue, which is this one, right? So we just create them as nil in the beginning, and then we just set them in the beginning to just create a make using the make queue API. So what is this lparallel API? So this is the lparallel library. We have used this before. I'm using this again. So this is the queues subpackage where you have this function make queue that we just saw. So it allows you to create a queue, and you can even set initial contents. We have none. And you can also set a capacity limit if you want. By default here, there is no limit. So that's what we're going with. We have no limit to our queue size. And we have the push queue and the pop queue. So that's what we will basically be using in our code, right? So this is how we first set up the queue, right? And then as we start the directory walking, we will keep pushing items. So that's where we go to this FS walker and individual files, and this is where the push queue is happening. So to this queue, which we have named for the main purpose, we are going to push this file name, correct? And when this is happening, because this code of pushing, before we have started this, we have already spawned our 4 worker threads. So those worker threads are running the process task function already, and they are in a loop. And in the loop, the first thing they're going to do is pop from this queue. So if you see here, this pop queue, it will remove the first element from the queue, obvious semantics, and also it blocks until an element is available. So if there is no element in the queue, it's going to keep waiting until the FS walker is going to produce an element and push it to the queue, and then this can pop it and work on it. And when this is working, the other threads, whoever is free, can go and take items from the queue. If all 4 workers in our case are busy, then the queue will just keep increasing until the workers are free and they can come back. So you might have seen in this design, there is a small problem, and the problem is because we have started the walker first, at the end of the walking process, it's going to like finish putting items onto the queue. We're going to have some number of items, n files, and if all of them are pushed in and the workers are popping, and in the end, when they reach the very end, there actually is no more information to work with. But we don't have a control flow here, right? We only have a data flow, and if the queue is empty, each of those worker is just going to do call pop queue, and pop queue is going to block, but there is no new element going to come up, right? How do we organize this? This is about thread synchronization. So our main thread knows that it's done, but the worker threads are still working, and when they're done and the queue is empty, they have to actually stop. But how do you do that, right? There is no easy way to do that. You need to have some kind of locks or some other design to synchronize your threads. So what I've done here is a very simple approach. So what I've done is, once we have done walking, which means we have pushed all the files into the queue, I will now loop for one time for each worker, and I'm going to push this simple keyword done into the same queue. So let's understand this clearly. This queue, the file system walker here will keep adding files to this queue, but at the end, after that is done, we are now adding this done, which is a symbol or a keyword really in Common Lisp. We're going to push 4 of those in this case onto the queue. And why are we doing this? This is not a file name, right? It's just a keyword. But the reason for doing this is, once the process task, if you look at the process task function, it will become immediately obvious. when the worker is going to pop an item, if the item is equal to done, it is going to return from that thread. So this will basically end the lifetime of that particular thread. So that worker thread will be closed, and this way, because we have 4 workers and we have actually put the tag done 4 times, each worker will wake up at one point and read that and end itself. So this will allow the process task threads, the worker threads, to basically shut down on their own instead of us having to do anything else to synchronize. So if you see here, immediately after this is done, we simply loop over the workers and we do a join thread. So this threading API is very standard in all languages. Basically you make thread, and then when you do a join thread, it's going to block on the thread. It's going to wait for that thread to end on its own accord. So it's not going to kill, it's going to just wait for the thread to complete. And if you see here, I have done an exact same logic with the print queue. So with the print queue also, now that we know that all the workers are done, there's not going to be any new print job. So since all these 4 workers are going to be closed, there is no way there is going to be a new print job coming up in this queue. Though this queue might already have like tens or however many items pending on a to-do list. We will simply put in one done tag into this queue, and when the print worker reaches the done tag, it means that it has processed all the items and that thread also can shut down. So that's where this join thread of the print worker comes in. So this is a bit about how we are managing our threads and our queues between our different responsible workers. Okay, so with this done, I need to only show you one core thing to complete this picture, and that is how does the individual grep work, right? So one of the workers has taken up a file name. That's great. Now what does it do? And it's a very simple algorithm. There is no parallelism, none of that. We are going to simply process line by line. So if you see here, we have this loop where we start out with setting line to read line. So basically we are just reading one line out of the stream, and the stream is just opening a file. So I don't know if I covered this earlier in our channel, but this is a very simple, straightforward way to open a file, where you're saying file is the file name and stream is the stream object associated with that file. And in this body, we can use stream and we can read lines and stuff with that stream. We only want to read stuff here. So we'll do a read line, and we just say that basically we return end of file when you're done, right? That's again a normal read line pattern. So we're going to loop until we reach end of file, and every time I'm just having this variable I to track my line number because I want to know which line this match is happening. So I am going to increment I to control line numbers, and we're going to then check if there is a match in that line. So we will talk separately about the match logic, but this is simply an extension of what we saw in a video on find. I'm using the same CL string match library. I will talk about that in a moment, but we are just checking if there's a match on that line, and if so, we are going to collect the results of that line. And if not, we'll just skip and we'll keep continuing, right? And this is how these results are collected. And when this entire file is done, so basically we process an entire file, and only then we make our file result structure and we pass it out into the print queue. So this write to the queue happens once per file at the end of the file. So this is a very simple non-parallel approach. So if I go to my for a moment, let's just look at the way we write. So if we go to my print, I'm looking for my result printer. Again here, it looks complicated now because there are some more things we've added to manage color, to manage buffering of output, and so on. So I recommend you go and see this function's evolution. So I recommend seeing the evolution of this code, because right now this code looks very complicated, but the core logic is the same. We're going to pop an item, and barring errors and barring when we're done and so on, we simply format the results of that file and we continue. So I have also done some extra buffering in a bit to improve performance. We will talk about that later, but the core logic is that, and how we format the file also. There is this extra code here which looks ugly because I have to split the string by part and color each part independently. So we see that this portion is white because that's the normal thing, and then this red portion is the match. So that's why you see there is all of this code here to split out the string and then again print it out correctly. How I'm coloring the strings is also very simple. This is the standard bash ANSI escape code for different colors, and I've just hard coded it for the colors that I need. It's a very simple approach. This is not even an external library, and that's how we are actually printing the results. So we saw a bunch of different things in this video. Of course, the code looks a bit complicated because it's an evolution of things, but the architecture is very simple. We have one thread to do your core file system, the main thread to do the file system walking and to manage other threads. We have queues to communicate between threads. We have a set of dedicated worker threads for the actual grep process, which happens per file, and we have the printer thread to do the printing.